I have to tell you, I haven't been as nervous since my first AGU talk. But fortunately, my message is very simple, and it's that even in the age of PBO and continuous GPS, campaign and semi-continuous GPS observations are crucial for mapping the velocity field in the western U.S. Clearly, we prefer to be able to have continuous GPS observations everywhere, but they're costly and we have to make compromises. This graph, this picture shows the campaign networks that we've established in the USGS over the last 10 years. They're cost-effective, simple, and produce very robust results, patient time-wise. They're labor-intensive, so we need lots of observers, but fortunately training is minimal, and observers are always welcome, and so if you're interested, please speak to me afterwards. This is a velocity field determined from our campaign measurements over a decadal period, basically in the interior western U.S. And you can see the consistency of the observations, and the error ellipses are about 1 millimeter a year. The PBO, of course, provides more accurate measurements, but they're concentrated near Cascadia and in California. And when you put the two data sets together, you have coverage that is very complementary. Recently, in the last 5 years, the group at UNR have developed a semi-continuous GPS observation strategy that combines the best of both methods, and I'll talk about that a little bit later. Whoops, missed one. So this is a typical GPS velocity field determined from campaign measurements, and you can see just from looking at the data that high velocity gradients are indicative of slip-on faults. We can model this with strain analysis or block models, but you can see it clearly in the data. Similarly, regions that are not deforming, in this case a rotating block in eastern Oregon, a region where the slippage on a fault is about a couple of millimeters a year. I am a real fan of the semi-continuous GPS network method that Jeff Blewett and his colleagues have developed. It combines the best of both methods, is cost-effective, and provides results that are just as good as continuous GPS. This is an area on the California-Nevada border. The red arrows are PBO. The blue dots are the semi-continuous sites. And you'll see in a minute, the high density of observations provides unparalleled detail that Bill Hammond and his students have used to determine slip rates on faults at the sub-millimeter a year level using block modeling. So my take-home points are that there's still a place today for campaign and especially semi-continuous GPS that is complementary to that provided by PBO. Secondly, that these methods can determine slip rates on faults that are slipping at less than 1 millimeter a year, which in some areas may be not very interesting. But in the interior west, it's part of the tectonics of the west, and it's important for hazard assessment. Thank you.